Spencer, is it
Milito.
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 Like with an E, but yeah. There's a whole story about that.
He's going to be talking to us about some of the bar graphs, and we're happy to have you, so take it away.
Alright, my name is Spencer Milito. I teach at Longwood High School. Energy bar charts are very topical because they ended up in the sample cluster, which I was very happy about. I've been teaching these to my students since my second year, which was last year, and it's a big deal in AP Physics 1 as one of the big models that they have to do in the FRQs. Okay, so now it's really coming over to us. And the region students really do end up actually getting this. They like doing this. What I give them at first, I do give them some of the content. So I give them this. It's just a fact sheet. My fact sheets are based on Greg Jacobs' teaching. So if you ever get the opportunity to go to one of his things, he does the AP Summer Institute and a Conceptual Physics Institute as well. And I can link those in my stuff and upload that as well. When he goes through all that as everything like this. What I give them is all the different types of energy. I don't like to stand up there and tell them all this stuff. I just hand this to them. And they have at the very bottom a constructing a work energy bar chart. So I go through all the steps. So they gotta make a sketch first and circle their system. And I'll show that on the board, or it's actually right here. They're gonna represent the energies in the initial state on the left side of the bar chart. So what we had in the sample cluster, if you're unfamiliar, there were two models. There was one, I think it was like model 1 or model 2 in there at the very top, and it gave you the amount of energy at one point in the system. I think it was like at the very top before the guy started to jump down. And then it gave it to you like right before the bungee cord stretched out. So how I actually end up having this is like this down here. We have a nice chart, left side and right side. What I put here is a dotted line to kind of show that work goes with the left side of the bar chart. Because work is the change in mechanical energy. I don't tell them straight away, I don't go through work equals FD until it actually comes up where like I push something with some force and I want to find that speed, because then they get married to that idea. I want to have that work is the change in mechanical energy, because then they know that that's what work is. So that goes to the left side. See down here on the bottom as well, I have initial plus change equals final. That tells me that the amount of bars on this part of the bar chart should equal to the final part of the bar chart to show that I have conservation of mechanical energy. Conservation energy in total. And what I have here in my sketch, I probably can see that as well. The initial portion here, what I have here is called Sketch and Translate. This comes from Eugenia Echidna. Her book is very good as well. She now has a physics forum that you can go through. But what I do here is sketch out what's happening. So this is a ball being thrown upwards. So that's initial position. I'm going to call that height 0. So I have height 0 meters there. I have the mass of the object and the initial speed of the object. You see how I circled everything here and included like a little box for Earth. So you have the ball Earth system, that situation. And then at the end, whatever height it's at, I put a little question mark next to that. Its final speed at the highest point would be 0. Still the same mass, still Earth in the system. This is kind of like writing out your givens, but just not like writing them in a line. So you're still kind of using guess method if you still want to go to that part. How do I actually have them introduce this? So I have an activity sheet, and I have copies if you want to pick that up, or we posted. And this was developed last year by John Meyer, who's one of my colleagues. But I did change it a little bit to have the sketch and translate portion of it. So there's this website called Universe and More. It has a bunch of little different activities on there, and they have an energy bar chart activity. So just at the beginning, before we even worry about using equations and solving things, I have them make energy bar charts from this. So, and they have a nice worksheet that goes along with it. This is great because it shows them a situation that is occurring, and it gives them an initial and a final state as to what types of energy are going to be in those states. Okay. So this is Felix, I forgot what his name was, Felix Baumgartner. I think this is jumping from the stratosphere into down to Earth. So you have an initial portion here, you can stop it at this point. So you can see that he's at rest. He's some height above his lowest point. To simplify this, I call his lowest point height 0 when they're making the bar chart. I'll show how that works in just a second. And you can see the final point. He's moving downwards. He's some height above the Earth, but just simplification, we'll call that 0. So the great thing about this, you can make your whole bar chart. So you have kinetic energy, gravitational potential energy, elastic potential energy, and internal when that actually comes up. You can add your work bar. Okay, so I tell them to put all these in here besides internal energy for the most part. And then I say, all right, at the beginning, I'll draw this over here. At the beginning, we're going to draw out the scenario. So I have, so at the beginning of the scenario, he has some mass, okay. He has some unknown height, but there is h, and his v initial is 0. He's at rest, and let's keep Earth in the system. And then I circle Earth, and I circle Felix because that was the system that I was given. Okay, and then I would write initial on the top. All right, so the initial side of the bar chart we can take from our sketch what we have. So he has some height. We have Earth in the system, so we're allowed to have gravitational potential energy. And as simple as I can do, and I gotta use the thing here, says, I'm just gonna give it 1 bar. I tell them it doesn't matter how many bars you give it, as long as they equal on both sides. Okay. So then we can look at the end. At the end, at the end he's moving, and we're gonna call that a 0 point for the height. Okay. So when I draw this, when I draw this now, I have him down here, and he's got some initial or some final speed, whatever that is. The height is 0. He still has a mass. So then we know we have some kind of speed, and we're at our 0 point. So at that point, I'm going to have kinetic energy. I don't have any work because the Earth is not an external force in this system. So I have the gravitational potential energy, the kinetic energy, and when I check, look at that, it works. Okay. If you make a mistake with this is what's great about this as well. I don't have to go around and like check them each time. If I make a mistake with this and then I say there's elastic potential energy for some reason. Make a mistake, it's going to tell me that conservation of energy has been broken, and it's going to say there's no spring there, or nothing that's stretching and compressing in the system. So it's going to tell you why you got this wrong. Or if I decided to throw work in here, it's going to tell me the same thing, that kind of thing. If I did this instead, it's also going to tell me that there's nothing that's external to the system, and network would be 0. And this is great for AP as well. So now, because I saw this in the sample cluster, this is something I did not do beforehand, but I will do it next year. They did talk about the system, the bungee cord, person-Earth system. So let's just see what it would be for Felix. It's the same scenario, I just would circle Earth back there. The same situation, you can pull out all of the energy bars here. And add your work bar. And the same deal, but with this, since Earth is no longer in the system, it becomes external to that. So, when I do the bar chart, I say we still have kinetic energy at the end, but what do I need for initial plus change equals final to work out? I need that work bar in the middle. So I put the work bar in there, and 1 bar again. I check, and there we go. All systems are complete. Okay, so they go through this, I take 3 periods of this, I introduce it to them with this one, explain it to them, and then they go off and do it on their own. I'll walk around the room and help them with this. But again, when they make a mistake, it will tell them what the problem is with it. And I have the whole worksheet here. It will tell them what system to use, make the sketch, and make their bar chart. And then once they, yes?
Sorry to interrupt. So you're saying on that website there are other ones, or you use that as the intro?
I use that as the intro, and on the website there's 14 different scenarios.
Oh, wow.
What's the name of that website?
Universe and more. They have other things. I'm going to email this person as well because I do momentum bar charts and see if they can make one like that. So that's not too bad. But there are 14 scenarios. I don't do all of them. Some of them are a little bit weird. But for the most part, we go through a lot of those. Once they finish with this, because some of them will then just fly through it, I go, all right, go to your fact sheet, look for the equations for these types of energy, and then set up the actual conservation of energy equation. So I make sure that they, because sometimes with this as well, when you get something that has 2 bars, they'll be like, okay, I put 2 in front of MGH. They have to get that gone right away. So just make sure that any set of bars gives you that equation below it. It's not based on the actual amount of bars for that one. So they go through this. This is 3 periods, and then I'll get into the actual lab for this. And my lab, so I do labs a little bit differently. How I do is I get a worksheet. There's 6 different exercises, and they get that first exercise, and they have to go and figure out something from that scenario. So this one, they were trying to find the speed at the bottom of like an inclined plane. So like with a smart cart, like a motion detector, any of those things, or there's simulations that you can do. So they're given the scenario, they have to then sketch that scenario. It's the same thing like we had earlier. This one, then they're going to actually solve for something. So this would be solving for the speed at the bottom of the incline, and they go through all of that. This one's very scaffolded at the beginning. Then towards the end, it will just say, make the sketch, make the bar chart, solve for what you're being asked to do. And I go through as well guess method here, because that was important with actually writing the gibbons with the units and things like that, but it doesn't seem as important based on the sample clusters that we were given. And then they go to Spark View for Pasco, but it'll be different like if you're for veneer, and they get the manipulated speed and the actual speed for that. I also went through and made a sample cluster. I think the Six Flags packet, if you have access to that, you can find that online, I can probably put it in here, is a really great source of like real data. So I took Superman Ultimate Flight, and they had a graph for altitude versus time, and I went through and made 5 questions based on this. This was the best picture I could find of it. I think there are better ones for that. But this is good because it gives you different points on this graph, and then you can find like the gravitational potential energy at certain points and things like that. So what I did, my questions were constructing an explanation from graph 1, figure out where the coaster train Earth system has the greatest amount of gravitational potential energy. So I didn't see ERC in the sample cluster, or a claim evidence reason. So I do it evidence reasoning claim, but whatever. But I didn't see that, so I made one like that. Then I photoshopped the bar chart from there and had them made this up here to kind of go with the bar chart that was in the sample cluster. And then the mathematical model, same thing from the sample cluster, and then a couple multiple choice. One of these that's based on the sample cluster as well. I pretty much just took that and changed up the questions for this, but this is also in my stuff there as well. But this didn't take too long when having the sample cluster in front of you, but I can imagine from scratch it takes a long time. I think that's pretty much it with this. So essentially with this, you kind of start off with conservation of energy first, and then if you need to get smaller, you do. But this is a really great website to get through all of that. And then once they finish this and they're able to put the equations on the bar chart, the rest of the unit is pretty much a breeze. They can use bar charts then for power as well. I still do the stair power lab, where you can get that the work is going to be equal to gravitational potential energy. You put that over the time that it takes them to get up the stairs, and so it goes throughout the entire unit. It's very applicable to NYSSLS, so that's really good. This is great as well for AP physics if you want to use it for that. That's pretty much it. Yeah.
Thank you for showing this. This is super cool. Are you saying that when this is how you start energy?
This is how I start energy.
You give them the fact sheet.
Yep.
You'll need this eventually. You'll need some of it eventually.
Yeah, they'll still need it to understand what types of energy. So when they have this in front of them, so it tells them kinetic energy 1/2 mv², mass of the object, the speed of the object. So if an object has some kind of speed, it has to have kinetic energy. Gravitational potential energy, that height is the vertical height above its lowest position. So then they know when it's at the lowest point, you put no bars for gravitational potential energy. So they have this in front of them. But I'm not going to stand up there and like go through all of these facts.
And you just start with those scenarios. I think
Yeah.
it's a great way to intro it and have them. In all of my years, I've learned more and more to trust the kids.
Yeah.
If you give them something engaging, they'll learn a lot.
Yeah, they
I
really
think
enjoy
this is
this,
really great.
and they love the different scenarios. Like there's one with Tony Hawk, in a loop, which is a little bit confused perspective, but then once they understand the perspective, they're great with it. There's Pendulum Ride from like Six Flags. That's like the Wonder Woman lasso ride, I think it is. But it goes through 14 different scenarios. They think it's all Human Slingshot. They love. Yeah, they love this one, and then that brings in elastic potential energy and everything. Kind of like the sample cluster with the funky code, but a much crazier version of it. Yeah, but they spend deep years on this, and they're great with it. You know, like I said, when it makes a mistake, it tells you what to fix. Yeah.
Have you also tried using, because I know FET also has energy barker simulations for like roller coasters. Have you also thought about using that as well so they can better, like, so as this is going like next to it, maybe as another like, intro thing for them, they could see how like in real time the energy changes?
Oh, let's talk about the energy skate park one?
Yeah.
I haven't done that one before, but I'm aware of it. So like if somebody needs to do like the lab and wasn't in school or is like on home tutoring, they could definitely use that.
Okay.
But yeah, I haven't done that one with this.
Okay.
Because once they get into the lab, then they kind of like see
Yeah.
the differences and everything. Yes.
You had mentioned earlier that there was a book in the forum, but I didn't think I got your.
So Eugenia Kidna brought on this board.
If you scroll down, I think he actually references her a little bit higher up.
Yeah, here.
There you go. College Physics Explore and Apply by Akinda and all the others.
Yeah, that's the book. Volume 2, if it's. I can't get it.
I think it's got a bicycle on the front. It's green.
You mentioned using this to show conservation momentum as well. Has that been successful before?
I made up a different like simulation with there was like these carts, a few particle I think it was. I can link that as well in my stuff. But he had like these carts where you could show like collisions. So I started off similar situation with this where even like the 6 different scenarios they made the bar charts. That was successful as well. Momentum is a little bit more difficult because there's different directions with everything, so it's a little bit more nuanced versus this where it's kind of like, all right, everything's positive, we don't have to really worry about positives and negatives. Momentum can get more difficult, but I do momentum first. So then when they come to this, they're like, oh, this is really easy. So the only thing I can see, which has started to happen, they kind of then confuse the both of them a little bit. So there's got to be a way that they fix that, but this is the first time I do momentum bar charts, so. But I think it was really helpful for them to, they were really good with conservation momentum this year. Any other questions?
All right, Spencer, thank you so much.